So here's the strategy for U substitution. What is the function that is stuck? And what is its derivative? We're going to let u equal the stuff, and du is the derivative of the stuff. We're going to substitute that all of the original variables become u's. So all of the x's have to disappear, and we're going to become u's. Then we're going to be able to integrate, and then you got to put at the final state when we solve, we're really sticking the stuff back in. Now, all that isn't going to make a whole lot of sense until we actually look at a problem. So what is the function, the stuff that is stuck? What is its derivative? U is going to be the stuff that is stuck. Du is going to be its derivative. We're going to substitute in. We're going to get all u's in our problem. Once we have substituted in, we can now integrate. And then we solve our final answer by sticking the stuff back in. Okay? So this is going to allow us to undo a chain rule more effectively than before. So we haven't really been able to do that. Now, again, if you can avoid the chain rule, if there's some way that, you remember when we did derivatives, when we were learning those derivatives, there were techniques that we were learning that we could make life easier. So if there's a way to rewrite it so you don't have a chain rule, do that. You don't want to use U substitution unless you really have to. Now, when we were doing some stuff in trig last year, and even I think maybe somewhere along the line this year, we had done a little bit of U substitution to get used to that kind of terminology and that kind of thinking. So we will actually be doing, I'll be showing you the technique as we go. So it isn't something that you necessarily should know right off the bat. So you want to kind of make this feel like a puzzle. What's the stuff and is its derivative somewhere in the problem? What's the stuff and is its derivative somewhere in the problem? Think about when we did that activity with the antiderivative stuff. You know, we kind of were thinking backwards. Well, we're thinking backwards for a U substitution. So you will notice that we have this quantity to the fourth. So what I look for is if this is my stuff that's stuck, because I don't want to have to multiply that 4 times, that's gross. If that's my stuff that's stuck, most likely that's going to be my U. And then we have to look, is a multiple of its derivative on the outside? Well, its derivative is 6x plus 0, 6x, which is a perfect match. It's not always going to be a perfect match, but at least has to be a multiple of an x. It has to be sitting there. So what we're going to do, you're going to rewrite that u equals 3x squared plus 4. Then you're going to put du equals 6x dx. You are going to write the dx this time, that change in x. And then we're going to substitute everything into the problem, including the dx. So it has to be a perfect match. So watch. This goes right there. That's going to be our u. It's a perfect substitution. This is a perfect substitution for both of those things. So you have to substitute not only the x's, but the dx as well. It becomes a du. So we're going to integrate u to the fourth du. Now we know how to do that. That's easy now. We know how to do that. That's just reversing our power rules, right? So we're going to get u to the fifth over 5 plus c. Now, our original problem had x's in it. Our final answer has to have x's in it. To solve it, we have to put it back in. So remember, our u is equal to 3x squared plus 4. That's going to go right there. So you're not done until you rewrite it as an x again. And so we're going to get the quantity of 3x squared plus 5 to the fifth, or plus 4. I was making everything 5s. 3x squared plus 4 to the fifth, all over 5 plus c. Now, how could we check this? Well, let's do a little check here. Are we right? Well, the derivative of an integral is the function inside. So if we take the derivative of that, we should see the function inside. And so let's do the derivative. The 5 would drop down in front. The power dropped down by 1. We would multiply by the derivative of the inside. Isn't that exactly what's sitting inside there? So you can check your work very quickly if the derivative of what you have is sitting inside. The derivative of an integral is the function inside. So if we want to check our work, and you sometimes can just kind of glance at it and think about what the derivative is. You don't have to necessarily do that on paper. But that is a perfect match. Okay. Let's do another one. So we have a z squared minus 5 stuck in something. Most of the time, that's where you're going to look for the stuff. So let's do a little rewrite. Let's make that z times z squared minus 5 to a power of 1 half. Okay. Z times the quantity of z squared minus 5 to the 1 half. So our stuff that appears to be stuck is our z squared minus 5. So let's try that. Well, the derivative of a z squared is a 2z, and I see a z to the first out there. Now the 2 is going to cause an issue, but we're going to fix it. We're going to make it work, and here's how we're going to make it work. We're going to do the derivative. du is 2z dz. Now, let's look in our problem. We only have in our problem a z and a dz left to sub in. So we need to get this side of our equation to say z dz, what's left in the problem. To do that, the 2 needs to just divide and go to the other side and become a 1 half. So now that we know 1 half du is equal to z dz, which is found in our problem. Okay, so we've got this z dz. We know what z dz is equal to. It's equal to 1 half du. So that comes out, and I usually put the 1 half in front of my integration symbol because it's a constant. It's just going to be there. And then we have du. And then we get u to the 1 half. Now we know how to integrate that, right? That's just undoing a power. And so we are going to, constant's going to stay there. Our u is going to go up to a 3/2 power, but we have to multiply by the reciprocal of 3/2, so we're going to multiply by 2/3. Now we're not done until we have actually simplified it a little bit, made it prettier, and then stuck the u back in. So we're going to get 1/3. This is what goes back in, z squared minus 5 to the 3/2 plus c. Now, we can check. If I take the derivative of that, the 3/2 drops down in front. Making it just 1 half. The stuff stays there. It would go down to the 1 half power, and then we multiply by 2z, and the 1 half and the 2z would cancel. So we could check our work. It does work. It is a perfect match. Okay. So that is that. Anybody have any questions about what we see there for example 531? Make some sense? Okay, let's try again. So here we have our integration. Remember, when some of the techniques we've learned about derivatives are very helpful for integration. So I would probably rewrite this as the sine of t times the cosine of t to the negative third power. So what seems to be stuck? What seems to be stuck inside of something?
T, I guess. The cosine.
Go further than, yes, the cosine. Is its derivative or a multiple of its derivative living in the problem? What is the derivative of a cosine?
The sine, but the sine would, wait.
It would be negative, so we are going to have to account for that. It only has to be a multiple of what there. If we have any numerical difference, like in the last problem we had a 2 that we had to get rid of by using a half, we're going to take care of that. As long as a multiple of its derivative is living in the problem, that's the correct choice for our U substitution. So we're going to let U be the cosine that's stuck. The du is going to be negative sine of t dt. Now, what was noticed was the fact that there is no negative in our problem. We just have a sine of t dt. So remember, you're going to get this right side to be a perfect match with what's sitting in the problem. The problem didn't have the negative. So what we're going to do is we're going to move the negative to the other side of the problem. Now, sine of t dt is equal to negative du. So these two things are going to come out, and that gets replaced with a negative du. This is going to come out, and it's going to be replaced with a cosine of t is going to be replaced with a u. So that's u to a negative 3. Okay, so now let's look what happened. Sine of t dt is equivalent to negative du. So we put in the problem negative du. Cosine is equivalent to u, so we took that out and made that u to the negative 3. Now, all of the variables in the problem that should contain, or the problem should only contain u's. And now we pretend like the first one didn't exist. We know how to integrate that, right? We're just going to use the power rule and go backwards. So how do we use the power rule? Well, the power is going to go up by 1, which would make that a negative 2. We already had a negative out in front. We have to divide by that new power. So it just so happens that the two negatives are going to turn into a positive. And so it's going to be u to the negative 2 over 2 plus c. And we're not done until we put the cosine back in. Now, u to the negative 2 is not how we normally leave things with negative powers. So I would suggest writing it like this. 1 over 2 times the cosine of t squared plus c. How could we check? We could do the derivative. You would get exactly what you see there. This 2 needs to be there so that when you drop that negative down in front, that negative 2 down in front, it cancels out. The negative that drops down in front, because this is in the bottom, cancels out the negative for the sign. So it all works out. If you did the derivative of this, you would get that. Whether you used the product or the quotient rule, or you fixed it and made it a little different. Any questions about 532?